Assalamu alaikum everyone. Welcome to our problem set solution. Our problem number is 1.2 and 3.1. My study partner Sharat Query is with me to solve this problem. I will present my part. My problem set number is 1.2. So let's start. My problem set is based on the convex preference. We can see here uh, on the basis on convex, there is a given convex utility function u of x, where x belongs to R plus n, denotes composition bundle with n components. In addition, consider the transformation b of x equal to f of u of x, where function is strictly increasing and convex. Now, we have to show that the preference represented by b of x must be convex. That is our problem. In case of solution, first of all, a question arises in our mind, what we needed to show. In order to show convex in preference, we need any three bundle x1, x2, and y that satisfy x1 rebel preference y, x2 rebel preference y, and their linear combination x equal ax alpha x1 plus 1 minus alpha x2 is satisfies x1 rebel preference y in terms of the utility function u of x representing the preference relation rebel preference. These properties implies that the utility function from bundle x1 and x2 satisfied u of x1 is greater than or equal u of y, and u of x2 is greater than or equal u of y2. That means the utility of the linear combination x is yields a utility level weakly higher than that of bundle y. Say for example, we can say that u of x is greater than equal u of y. Now we see the proof of that transformation problem. Here we can see a graph, convex utility function. Let's try to solution the problem with this graph. Since the transformation v of x equal to f of u of x is convex, um, if satisfied v of x equal or greater than alpha v of x1 plus 1 minus alpha v of x2, in words we can say that in that graph we can see that that is our that is our convex curve, convex utility curve, when the utility of x1 uh, intersected this point and utility of x2 in this point. mm, from bundle x1 to x2, uh, with their linear combination, we can see that v of x greater than or equal alpha v of x1, alpha v of x1 plus 1 minus alpha v of x2, uh, as depicted in figure 1.2. We can see, using the definition of transformation v of x equal to f of u of x, we can rewrite about inequalities in terms of the function rather than in term of v of as follow: f of u of x greater than or equal alpha f of u of x1 plus 1 minus alpha f of u of x2. In addition, since transformation f of u of x is strictly increasing, f of u of x1 is greater than or equal to f of u of y. Since u of xy is greater than u of y, similarly we can say that f of u of x2 is greater than or equal f of u of y. Since u of x2 is greater than u of y, hence we can expand the above inequality as follow: f of u of x is greater than or equal alpha f of u of x1 plus 1 minus alpha f of u of x2 is greater than or equal alpha f of u of y plus 1 minus alpha f of u of y equal f of u of y, which simplifies to the f of e of x is greater than or equal f of e of y. Finally, using again the property, the transformation f of e of x is strictly increasing, f of e of x is greater than f of e of y implies u of x is greater than equal u of y. That is the solve of this problem. That is my part. I requested to query to present her next present his next part.
Thank you, Masood, for your nice explanation. I am Sharad. My problem set number is 3.1, which is based on corner competition. Let's start. And here we consider a inverse demand curve PQ equal 10 minus Q. Uh, farm 1 and farm 1 output level is Q1 and farm 2 output level is Q2. And two farms selling a homogeneous product simultaneously. So part A, uh, part A, one that one that when two funds marginal cost is same, find out the each fund's equilibrium, each fund's output equilibrium, and uh, part B, farm to invest in cross-selling technology. So farm two's marginal cost is decreases, and we repeat our analysis in part A with their new cost function for farm 2, assuming for farm 1's cost function is unaffected. And in part C, we compare part A and part B. Next. Next. And in part A, in finding farm I's best response function, every farm I belongs to 1 and 2. Solve this following profit maximization problem. Maximization profit. This is revenue part and this is cost part. Uh, and after this, we can find this equation, and uh, we want to maximize our profit, uh, taking the first order condition with respect to Qi, and assuming an interior solution for Qi, and 6 minus 2 Qi minus uh, Qj equal 0 if Qi greater than or equal to 0. After rearranging the best response function of farm I in response to farm J is given by next. And this is the farm I's best response function, where and vertical intercept at 3 and slope of minus half. Specifically, letting farm 1 be I and farm 2 be J. The best response function of farm 1 becomes, this is the farm 1's best response function. In figure 3.1 shows farm 1 best response curve depicted in the downward line. When farm 2 produces no output, that is Q equals 0, the best response of farm 1 is to produce 3 units of output as depicted in the vertical axis of figure 3.1, whereas when farm 2 produces 6 or more units of output, since farm 1's output cannot be negative. The best response of farm 1 is to produce 0 units of output as depicted in the horizontal axis. Similarly, letting farm 1 be J and farm 2 be I, the best response function of farm 2 becomes, this is the farm 2's best response function. Next. In figure 3.2, we simultaneously see farm 1 and farm 2 best response function. So, farm 2's best response part being depicted in blue line. Blue line, this is the line. And therefore, when farm 1 produces no output, that is Q2 equal to 0. The best response of farm 2 is to produce 3 units. This is the point, as depicted in horizontal axis of figure 3.2. When farm 1 produces 6 or more units of output, since farm 2's output cannot be negative, the best response of farm 2 is to produce 0 units of output exhibited in the vertical line. This is next. Using BRF, best response function to find the mesh equilibrium, the intersection between the two farms best response function represents the next equilibrium output pair in this gate. To find this crossing point, we can simply substitute the best response function of farm 1 into the farm 2. And after manipulating, we find this Q2 divided by 4 equal to 3 by 2. And after solution, we after solution in farm 2 equilibrium output is 2 units. Next, substituting the equilibrium output of farm 2, the farm 2 best response function of farm 1 is P1 equal to 2. Means next, as a result, both farms produce the same unit of output in equilibrium. Graphically, we can see in this in figure 3.2. And so, and in part B, in finding farms to best response function, while the profit maximization problem of farm 1 remains unchanged, that for farm 2 changes because of investment in cost-saving technology. In particular, farm 2 uses Q2 to solve the following profit maximization problem. This is revenue part and this is cost part. And after manipulating, we find this equation. Next, to profit maximization, we can take first order condition with respect to Q2 and assuming a intermediate solution for Q2. And this is the equation we find after manipulating and after rearranging the best response function of farm 2 in respect to farm 1, we can find the farm 2 best response function, which is now originates at a vertical intercept of 4 above the vertical intercept in the previous setting and still has the same slope of -half. Intuitively, for a given output of farm 1, farm 2 produces a larger output due to its lower cost. The best response graphs are depicted in figure 3.3. Next. In figure 3.3, we simultaneously see farm 1's best response function and farm 2 best response function. And the equivalent point is this point, where two best response function graphs are crossing each other. So, using the best response function to find the next equivalent graph, substituting the best response function of farm 1 into the best response function of farm 2. After manipulating, we find the farm 2's equilibrium output is 3 into 1 by 3. Next, substituting the optimal output of farm 2, the best response function of farm 1 is this 1 into 1 divided by 3. As a result, farm 1 produced 1.33 units, while farm 2 produced 3.33 units in equilibrium. Graphically, we see the intersection of the best response graph in figure 3.3. In part C, we compare the part A and part B output. So, when both farms are symmetric in cost, each farm produces 2 units of output, whereas when it becomes less expensive for farm 2 to produce the output, farm 2 expands production from 2 to 3.33 units, and farm 1 best response is to production from 2 to 1.33 units. That is our solution. Thank you for cooperating with us. I hope you will enjoy our explanation. Bye.
Thank you everyone to cooperate with us and hope that all of you enjoy the video. And this is our part, problem set 1.2 and 3.1. Me and my study partner Sharat Kari was with you at that time. Hope that this video will helpful for you to progress in your